departments there. He works in various aspects of scientific visualization for basic research to develop applications in real world disciplines. So Ingrid is here as the Professor Ram Kumar visiting chair at IISc. Today, Ingrid will be telling us about tensor-valued visualization. Over to you.
Hello, everybody. I hope you can hear me. So, thank you for your introduction. Welcome everybody to my talk. So when I was preparing or thinking about what I should talk about, I would like to avoid any overlap when I go here. Then I thought probably I put something that is with me for a very long time already, almost my career, which is tensor-valued. While preparing the talk, I also realized that we don't really talk much about tensor-valued visualization, but I thought a lot about a question that pops up again and again when working in this area. And this is it even possible to have a simple visualization of complex data for tensor-valued visualization? So that you get a little bit of a better idea what I mean with this. I want to give you some background about my research interests. So what you see here is the visualization center in Schöpping, where I'm situated. I'm leading the scientific visualization group. With this, I'm one of 6 groups dealing with visualization, which already shows how many different aspects you can consider in the area of visualization. And what my group and me are mostly interested in is the aspect of data analysis using visual methods. And in contrast to automatic methods, we really want to keep the user, in our case, mostly the scientist, in the loop. And the main goal is to help the scientists better understand the data. And while in many cases, really the goal is to make analysis fast, I think our goal is probably somehow even the opposite. I would like that people are able to spend a lot of time with the data, engage with the data, and to the data reason about what it would mean. The kind of data that we are typically dealing with are so-called something that we call multi-fields. This means we have some spatial context. Typically, we have a spatial domain. Every point in the domain is mapped to some attributes. For example, you can think here with the room, and every point in this room, I can assign a temperature value, I can assign a pressure value maybe. Here I also maybe even assign velocity vector, which tells me something about the wind speed in the room that's generated by our fans. So this can be a combination of scalar fields, vector fields, and also other fields. In many cases, these are time-dependent data sets, also that you can even in series, and we have additional parameters describing the data set. And they have typically also some geometric information provided. This could, for example, be the rotating propellers that we have here, where we have the geometry of, and for sure some metadata. So I think I stands here for an interval representing the time, and P can be any parameter space that we think about. For example, if you run an ensemble, maybe from a simulation, there are simulation parameters. They're running it again and again. I did not highlight it here, as I will not talk much about these things. I mean, more the important things that we have a domain, which is more the spatial domain, and we have something that I, in the following call attribute space, my attributes are somehow collected in possibly the information space. When we are generating visualization, in most cases, we are somehow driven by an approach. Then we spend a lot of time thinking about good visualization concepts. How can we find good metaphors, good mappings? for the data, mostly with a goal to go beyond the application. It's going more to design new visualization concept, maybe inspired by this application. Then most of the time we spend just developing algorithms to make to find efficient, reliable, and robust implementations of what we develop in these concepts. I will talk about today. It's only talking about visualization concepts. We will not talk about algorithms, and we will also not talk much about applications. So, as the goal, they have to think about when you find simple visualization methods, even for possibly complex data, which most real-world data is. I thought I'd start looking at some examples of visualizations that are considered as being successful, and whether we can learn them. My first example is something that probably everybody of you have seen 10,000 times. This is just the map. This is from a German newspaper, so therefore it's Europe-centric here. And maybe I don't have to say anything about this visualization. What makes it successful, you look at it, you understand it without any explanation. Anyways, let's have a look at what is actually happening here. So we have temperature, which is shown as a color map. We have pressure, which is shown by contours. We have a little bit of topology here, shown by the maxima and the minima. We are highlighted as H and T, so we have high pressure, and here we have a minimum in the pressure, and then there are all kinds of additional symbols to help. What I really like about this visualization is not that you can understand that. So when I get that all the way, these methods that are shown here is basically everything that is out there that is really used. So this is total representation. For sure, we have similar things in this language. What you see here in this picture on the left side, this is an isosurface rendering of a turbulent flow. As an isosurface here is rendered of electricity, which is generalization of the contours that you saw before. What you see here on the right side is something that we call a volume rendering. This is generalization of the color map. So what you have here is a CT data set. In comparison to the color maps, we do not just map color to every scalar value. For every scalar value, we also need now something like opacity. In many cases, we even map more optical properties, and then there's some optical model to render this image. In this case, really convex, so this is called kind of a photon mapping approach. And also, this is not driven visualization. If you think about that, this data set is more than 30 gigabytes. If you have interactive visualization, these are challenging things, but the user doesn't see it. These are things that happen in the background. If you look at these images, I don't have to explain much. Everybody knows immediately what's going on here. Probably you do not know exactly what sees mean in flow, but maybe you can still imagine what an isosurface is. I want to look a little bit more in the volume rendering method to think about what makes this method actually successful. So on the one hand side, okay, we have a high quality rendering here, which is kind of how, but I think what is much more important is to think about what to render. This is determined by something that we call the transfer function. This is the mapping of the scalar value here to our optical properties. What you see here on the image, this is also a CT image. So for Gabriel Men's assembly, which is shown in the British Museum. Actually, this visualization is also shown in the British Museum, and millions of people per year are looking at this visualization. What is nice here, you have one data set, but you see many different things depending on what kind of transfer function you choose. So here there's an emphasis on bone, and here is an emphasis on the skin. This is always the same data set, but just using different transfer functions to dig out different aspects of your data set. Interaction is also important. It's again a picture from our museum in shopping. People explore brain, so fMRI. How to allow people who interact with the transfer functions themselves. So what you see here is a simple editor for a transfer function where you have here a scalar value. Here you assign capacity. Now we can kind of move these points around. We can change color. We also can make it more or less transparent to get kind of different impressions of the data set. So this is still intuitive. It might have opinions. Already requires some experience to get kind of a good presentation. So, a lot of nice success stories like this for scalar data. The ideas are typically easy to communicate and to capture. But when we are looking a little bit closer, all these stories are again and again about isosurfaces, oil rendering, maybe a little bit of topology, which happens behind the scenes, which is not seen by the user, which helps with the watch. And now, for us, the motivation was, wouldn't it be nice to have such methods also more scale? And so when you are looking, for example, at tensor fields or multi-fields, there are hardly any methods that are widely used. Those methods that are there are very domain specific, group specific, often developed for one research group, used by a few people, typically only use having visualization experts around. As soon as we are leaving, going out of the door, they take the picture, put it in the paper, but they hardly ever use these things themselves. As it's a complex aspects, and often I really have a hard time to explain. So, before I start talking about what we did with the idea of generalizing these methods, I will very briefly talk about the kind of paper I would get. These are multi-field, and more specifically, also. I already explained what a multi-field is in the beginning. You can see this kind of representation again and again during the entire talk. On the left-hand side, I always represent kind of our spatial domain, which would be here our loop. On the right-hand side, I typically represent some representation of an attribute space, which is only an abstract representation. So if the attribute space is one dimension, we have scalar fields. It's two-dimensional because the bivariate, and then everything can fit. The other part is tensor fields. So when I say tensor fields, I actually do not mean tensor fields. I mean symmetric second-order tensor fields, mostly in three-dimensional. And for those of you who don't remember what this was, I have here one quick recap so you can understand the tensor is a linear operator which maps one vector to another vector in a linear fashion. If you do this for a lot of vectors spanning unit sphere, you will in the end transform unit sphere and get something like an ellipsoid effect. If you have a different sequence, you can represent it as a matrix, a 3 matrix with 6 independent components. And then very important for many visualization methods is you can decompose the tensor represented as eigenvectors with eigenvalues. We often refer to the eigenvectors as a direction and the eigenvalues as a shape of the tensor. So to motivate this a little bit, so the shape of this ellipse is really determined by eigenvalues, which gives you basically here the radii of this ellipsoid, and the eigenvector determine just orientation. And to some extent, you can understand the tensor field as a linear large data set. looking at all 6 components. However, you have to be very, very careful here because these components have certain relations. So they have to follow certain transformation properties, and it can be very dangerous just to completely ignore that there's a tensor field. Something that we also only use when we are visualizing tensor field, something that we call the tensor invariant space or the shape space that is spanned here just by our eigenvalues. So, typical tensor visualization has at least have to give a short overview. It's using glyphs. There's an entire zone. Everybody uses something different. There are a lot of textures which focus on the directional aspects of tensors. Here, they are restricted to two-dimensional slices. This is nothing that you can use in 3D. A lot of statistical plots. I look at these plots and say, oh my God, this doesn't tell me anything. No surprise. These are very specific plots. Here, these are more diagrams that are plotted as a statistic of an entire data set, which is coming in some groups of mechanical engineering to use, and this is a directional scalar plot for the directions. This is probably what you see most likely in the application, that you just drive a scalar field and just come up with it.
So you are basically a tensor term.
Yes.
How does the capital T give you values in the 3D space?
Well, that's okay. So I would say for every point in space, yeah, I have such a tensor. And an example is probably
Tensor is just think of it as
the tensor is in this case a second order tensor, which you can just think about it. Yeah, think about that in every point in space, you have a matrix given. I do not really like talking about a matrix because a matrix is only requires also some kind of nice representation. And I think the tensor can be presented as many different matrices. So, but really practical, what we have a data set, we have typically a grid in 3 dimensions where we have this value and every grid we have given
what are these two?
This is just one tensor. I would represent tensor probably as an ellipsoid. Just want to tell you how mathematically we would define tensor as a mapping from vector space to vector space. So there are other definitions which are equivalent, and this means the tensor is actually this entire map. What you would represent is probably this ellipsoid in any point of grading. And
every point is a map. Every point has
in every point of grading. And probably this becomes a little bit clearer. So now I want to look here at one really data set. So this is a clock, and at every point of this clock, we have a tensor. This is actually a data set from mechanical engineering. So you have here a pulling force, you have here a pushing force, and every of these glyphs represents the state configuration in this point. But what you immediately see, this visualization is completely useless. So tensors, you cannot even detect the glyphs that you see here. Glyphs have a lot of use, probably not in this way. This is rather to demonstrate that this is probably not the right way to go. This is probably the glyph that I would say, from a mathematical point of view, be quite complete to the center tensor, but it's not very frequently used in the applications. This is an example for another glyph that probably nobody knows here, and you'll see it's already complicated to explain. So you people here from mechanical engineering might understand what I'm saying. This represents a stress state. So the direction, so the red part refers to tensile forces in these directions. The extents is the strength of the tensile force in this direction. In part is compressive forces in that direction, and also create parts representing shear stresses. So if you have look at a certain normal, then the length of the extent here, this is the strength of the shear stress. You see already how much time you need to explain this, and probably nobody understands how you are supposed to read these things. But I just wanted to show this here because I will use it during my later slides. So these are the applications that we have been looking at. The strongest is by far mechanical engineering. We are looking into simulations of stress propagations. Here, for example, this is a hand brake lever from a bike. And you see these lines are supposed to show the stress propagation inside the brake lever. We have been looking at diffusion MRI, but the goal is to reconstruct fibers and use a frame from diffusion tensors. The geometry tensor plays a big role in remeshing, where we use tensor field topology. The last example is image analysis. Like everybody knows it's a structure tensor, tells you a lot about edges, ridges, and so on. This is just to give you one thing that I probably should mention. So I have a long ongoing collaboration with mechanical engineers. And once in a while, this of my friends say, can't you just show me the isosurface of the tensor? Yeah. This is what we're doing. And in this project, we developed something that we call interlens. The goal is here to generalize the idea of isosurfaces to more general data. But to explain the idea behind it, I'd like to start with scalar field, what is actually an isosurface. Then you have here a spatial domain. Now you see here isosurfaces. It's actually some density distribution in molecule. And on the right side, you see the attribute space, which is one-dimensional. Every of these dots represents one iso value that is here kind of shown as these nested isosurfaces. And what we have here is an iso value, and these surfaces are just a pre-image of this iso value. Now we can just increase the dimensionality of our attribute space going to 2 dimensions. And then we can again pick a point, say this is our iso value, look at our pre-image. Now we don't have a surface anymore. We get more or less a line, which is also called fiber. This is actually something that's also pretty frequently used in this application. Now we further increase the dimension of our attribute space. We pick a point. What happens? Typically, your pre-image will be empty. And if it's not empty, you might find some individual points. Followed in this organization for a long time, but without much success. There are some quite complex methods that develop out of it. So we thought we have to do probably something. Explain the idea and like to go through an example, which is more a broad example. Here our domain is 2-dimensional. Just think about I would like field and we draw drops, and we think of a multi-field describes the conditions for these drops to draw, which could be temperature, this could be wind, or whatever. So this is all made up. So don't take this too serious. Just to show the idea. Here's our domain, here's our attribute space. We start with the temperature. We might have a critical temperature where we say, okay, it's getting colder, it's not good for flows. What we do, we can plot here in 2D contour, which divides our domain in 2 parts. One part is values are larger, and things might go well. Then we have one part of things is smaller. Now we are looking at wind speed. Again, we have a critical value here. We draw another contour. Think about, yeah, maybe divides in two parts, each bad. Then we can kind of look at our one point here. Here our pre-image would be these 2 points which are not very important. So there are all kinds how we can combine these two conditions. So maybe we want to look at either or one of them is fulfilled. We even might think about a want set. One of the conditions is fulfilled smaller as larger as. Also could say we would have that those conditions are fulfilled, and this is already much more informative. So now probably going away from this specific example, in general, I would claim that many, if you have some idea what is an ideal condition or what is a critical condition, could be described as a subset of our attribute space. Here it's a two-dimensional space, this would also be a higher dimensional space, and then we look at the preset. Sure, still this can be empty. But maybe our props will also show if it's kind of okay. So what we are looking at here is kind of a distance field in our attribute space. And saying, okay, we do not illustrate the ideal conditions, but we illustrate how close do we get actually to these conditions. First, then we can pull this back. That's the goodness, the feature strength. This is the basic idea of the feature. Make it a little bit more formal. Something first I would like to define what we understand in the term of feature. A feature is something that is widely used in different contexts. Often having something in mind is something interesting. For us, it should also be something interesting, but we consider it as a part of the domain. And something part of the attribute space, we call that trait. And as mentioned before, often you can find kind of traits to define your features in your space, and then we call this trait introduce feature space features if there exists such a correlation. And if you think a little bit about it, many of these features of interest that are used in visualization can be somehow formulated in this way. So this leads to the definition in the end of our feature level set. So given it's a function from the domain attribute space, if D is the domain, A is our m-dimensional. Something that's really important, we need a metric space. And we can measure distances. So this is our domain, this is our mapping attribute space. Now we take a trait in attribute space, we define a distance field with a mapping to R. Then we have kind of this induced distance field in our domain, which we call kind of induced distance field, for which we then can compute level sets as before, giving us something information about feature strengths. This is, we call this induced distance field. This is the distance field. If you think about every point in my attribute space gets assigned one scalar value, which is the distance from my point. The distance from this trait. And this just gives mapping, and then we can kind of just, instead of going this entire way, can have directly a mapping from our domain into this case. Distances. This is actually, the distance is probably the most difficult part, and then you need a metric in attribute space. In many cases, we are using Euclidean distance. Sometimes it's good, sometimes it's good. Please come back to there are special cases for sure, which includes standard isosurfaces. There, the trait is just a point on my line. Something that is called fiber surfaces. Maybe people from visualization can relate to that. It's also kind of that we have instead of a point, we have a line. If we look at the three images, look at the surface, we can model this as a zero level set of the point line. So I only have one example here, but I would like to show some more ideas, and this is what really motivates us. The question, can't you just show me the surface? And I use this data set. My correlation models don't like this data set. It's really a true data set, and it's really, really simple, but we know the data set very well. That's the purpose to try stuff out. So here we have the solid block, solid material. We have here pulling force and pushing force. And what is rendered here is the directions of the stress for one surface if you project it. And here you have a volume rendering of the maximum eigenvalue. And the color refers to the sign when you have something compressive. So now we are picking one specific tensor. That's the reason why I wanted to show the cliff before, because they always represent one specific tensor using this kind of famous cliff, which is good for the stress. This corresponds to one point in the space. And what you see here in these renderings, you see a lot of level sets here. Red means it's close, green means it's a little bit far. So here on the side you see a colony. Dark red means it's really exactly the same as my tensor that is given. And you see this is only the case in two positions. And then we have kind of different level sets showing this. So you can pick two of these tensors. This is kind of interesting because they have the same shape, the cliffs. It's just one time you have compressive and one time you have inward forces. Then you get really nice symmetric behavior of the two forces your data set. And then if you would also be interested in the direction of the tensor, for sure you can add some direction also into your attribute space. And here the highlight regions is vertical major stresses which have this form. This is, for example, interesting if you are drilling a hole into the ground and you would like whether the walls are stable or they are breaks of drilling. So, two main questions are left with you here as configure the stage. So what is it? Here for the level sets, just pick one point. This may be easy, but otherwise this might also be a challenge already. And then also the second question, which level set to show. So now we showed a lot of things. This also leads to global presentation. I would like to focus next on this question to which level sets to show. And this again can be understood as a generalization of one method that we are using in scalar field, visualization of plot. This is something of scalar field topology, and specifically this refers to something that we call measuring. I'll start with briefly introducing the measuring. So you have seen this data set before. This is the data set of the density field of the molecule. And we are doing now, so here this bar highlights the ISO value that is represented here. And now we are not thinking in terms of this isosurfaces, but we are thinking in terms of sub-level set. This means we are considering the entire field ball here. So this is the pre-image of this entire. Now we are changing this ISO value step by step, and then we can observe how this surface here is changing. What we can see here there's not much change in a long time. But at some point here, when we are passing in the screen, it's all of a sudden a new component. This is something in the values that we consider as interesting. And this is something that we keep track of, which will then finally be encoded in a tree. This tree is a summarization of the entire data set, so the leaves in the tree represent always something that we call the birth of a component, and a new component emerges. Where these leaves are getting together, these are so-called zeta points. This would be here, for example, this component and this component are here kind of joined together, and we're getting one component. Then we will have kind of a few of these events until we finally release them. This is something that we call a match tree, which is really very useful for the action in order to decide what kind of level to show, and also to consider the concept of value. I have another slide kind of summarizing all of this. Now this is a three-dimensional data set. Think about the domain is just the ground here. And if it's a two-dimensional data set, then it's represented as a height field. So this is a height field of my data set. And we can say for all these uniformly colored areas, the contours have the same shape. So here's a contour, it's a circle. So this is the top view. If you look when you're only at the domain, the entire green area has the contour here is just a big circle. Then you see there are these center points, these are the events present the changes. And this gives you a segmentation to the entire domain, terms of very similar behavior, which is here then represented in this tree. So this green part is kind of the root of the tree, and then you can easily just select one of these things that we call these are feature classes. This is good for redaction, this is good for automatic tensor function design, and it's also good to remove noise because these little peaks here represent these small edges in the tree. You can do the kind of edges in the tree with respect to a certain threshold with cleans.
Edges, which tree represent different contours?
Exactly. So each of these edges represents a lot of contours. So this edge represents all contours in this area, which would be the outer part is getting closer and closer to the inner part. When we are reaching this point, this is when the contour is really the black boundary, the inner boundary of the tree. Then we are in this point. And if we now go a little bit up, then we will have two disconnected. This would be the yellow one around this little bubble. This would be one in this area and one in there. This means if I pick one of these edges in the tree, I get specifically one of these colors. In this case, we even can do this for very high data set. Sure, the computation is getting more complex. These dimensions. The concept is very so, from a more formal point of view, how we formalize this problem is we say in your tree we have some main ingredients. One is that we have an interval in attribute space, which is a sub-level set in our domain. This is just a sketch to give an idea of what this means. Then we have something, we consider this as a trait. This we consider as our trait indigenous feature. Then we have something that we call the filtration function. This is what is the sweep that let's say, okay, I change the ISO level. This could refer to a density. This could refer to a temperature. Whatever you do. And this filtration basically in the end fills up the tree. We will get a nested set of feature classes. Now the generalization to feature classes is actually pretty straightforward. Instead of having an interval, as we had before, we now have a general trait. attribute space. Instead of the sublevel that here, we will have our trait introduce features that have like all kinds of different shapes. And for the filtration function, we are looking at the density field around it, and we are filtering our function across the density value here. Then we also get kind of a nested set of features. So this is just again writing it down. A fixed trait, which is a subset. We have the trait introduced distance field. We then look at the changes in topology in our pre-image of our sublevel set. Spatial case is for sure the notch tree dimension. The trait is just the deepest point, and then we can filter the distance here. We also can put the point on the top. We also can put it anywhere in our attribute space, so it already provides much more flexibility as a original. Here, case study for multivariate field. And this is an application that we have been working with a lot over the last years. This is the interaction of the electronic density or interaction of the molecule with light. And typically, maybe you remember from chemistry, if you have a molecule and you are shining light of it, although you have changed maybe your electrons will be excited and change the orbital. So from a chemistry point of view, this means that the density distribution of the electronic field changes. Before you have interactions, after you have interactions. What you see here is probably recognize some balls that are connected. This represents our molecule that we have here. And so the blue bubble is an isosurface rendering of the electronic density field 4, and the red one is an is awesome. So I'm not very precise in the chemical formulation here, but otherwise it's coming too complicated to explain. The chemist calls this a whole entity and a part of entity. You just can think about this as before, and this is after. And we played around with a lot of different methods here. One thing is iron field. This means every point in the domain, we have now two scalar values, one scalar value, density 4, one scalar value, density. So we have two-dimensional attribute space here. The x-axis, this is our before value, the y-axis is after value, and what you see here is a kind of a scatter plot, something that we call a dense scatter plot. And if you want to think about how this is assembled, you take any point in your domain and check those values. Here maybe the red is high, the blue is low, so you would point here. If you do this for every point in your data set, resemble that kind of density distribution in your attribute space. This is basically only to give you a little bit of reference about how the data is distributed. Oh, here's color. These are the two different fields. I just overlaid them with one. Oh, here's the color. It's a number of points of flows here. This is basically density. Who means there are a lot of points. You see, we have a lot of points in the data set where both fields are 0. This is from the outer part of this data set. Both fields are close to 0. And this all connects. Actually, much more interesting is this yellow part. These parts, when you see, okay, here, there is some density after, but before density is zero. This is exactly what chemists are interested in. And this is the question, which area in my molecule are dominating charge, so giving charge way through the interaction, and which parts are accepting. What does it mean, being a dominant? Meaning you have a high value before and mostly zero value. This can be expressed by these points on our x-axis, so after 0 and or before is high. And we don't care whether this really exists in our data set. Just say, okay, this really doesn't have to be appropriate position. These are here our traits. Now we are using this trait-induced merge tree and look at the feature classes. The feature classes. In this case, we have kind of two areas pretty close to the center. You might say this is not a nice rendering. This is not a nice rendering purpose. So this is here we color every box that belongs to a certain feature class. What we have here at the bottom in the legend, this tells me how close does this class actually get to the trait that we introduced. If we now change our trait, something that we call vector trait, it's just the opposite. In the beginning, 0, so the x value is 0, and after the value is high, then we get here 3 different classes that we know these are things that mostly dominate charges. If you want to compare these different areas, you can look at these numbers telling you how close to get these traits that we have introduced here. I have a few more examples and then jump over them now. I just want to say one question that still remains here is how do we define traits? And I only have a few notes. We also worked a lot on this, and I just give you some examples. For tensor fields, we have a manual selection when we are running glyphs, for example, for slice. People can pick it and say, I would like to see there a small area. But you also can design your glyphs as a little kind of tensor generator of each of these axes, because there is one of the eigenvectors, and you just can pull around, and then you get immediately shown how the corresponding glyphs. Material breaks, do a kind of a failure analysis. Depending on the material, you typically have some yield surfaces. These are specific configurations in the attribute space. This is an example for one of these surfaces that we just picked from an actual paper here. Then you can use this as a trait and say how critical, show me how critical different regions in your material are. We also use clustering in attribute space. This is again stress distribution. Sometimes you have clusters. Most don't have clusters. Most this is only partitioning. It's a question whether there are any use in these things that we are currently working on, that we are using dictionary learning for class representation, get data specific basis functions, just here example for really now 64-dimensional space related to diffusion image. As in the action, show our clusters here in the tree map. So every cluster is represented as a square. The size represents the size of the cluster. The glyph represents the centroid of our cluster. And if we want to know what is the distribution of the values in the cluster, we also do a PCA analysis for every cluster. We represent here the centroid and the variance for different PCA. And then we also use parallel coordinates. This is very common visualization. Most people do not know it. So there we take every axis attribute space and place them in parallel. And every point in my spatial domain finds the one line here. Instead of having one point in attribute space, it kind of connects temperature, pressure, divergence, electricity, and so on. It's a line. You can represent your entire data set This is a slide also showing you a lot of distribution of these values. Again, this gives you some context about the distribution of your data and the data set. Then you can use this to define. Now these would be cubical traits only. You can define arbitrary intervals for all these dimensions. That's especially good for critical. I had to add this picture because I didn't talk about the generalization of volume rendering. I also did a lot in the area of trying to get a volume rendering specifically for tensor fields. You do not only have to design a transfer function, you also have to deliver what you want to show. And there you have the transfer function texture, you have the transfer function for volume rendering, and the transfer function for the lips. This is again our 2-point load. Now randomly putting together some information. So, in summary, I think many of the successful methods in scalar field visualization can be somehow modeled as an interplay between the main cubic space and the array. And by structuring the main, this is mostly due to features, get hold of not of what to show in terms of element sets or what transfer function, and if you structure your attribute space, it might help you to design your traits. Then somehow controlling the interplay between things. This can also be by interactively linking a lot of different windows. Sure. You can decide this is simply not, maybe not, I don't know. But there are some things where critical design decisions. I think the choice of the attribute space, of the in-memory space, is really the exception. Especially in particular for the tensor fields here. Every community uses different invariants. Most people don't use just people are looking, for example, at some shear. So they're looking at the determinant. They're looking at the traits. And can build all kind of invariant spaces out of the 3 parameters, which is not necessarily an orthogonal transformation of the space. Providing the right access helps people to design what they want to see. And this means they have to adapt the language of the domain, makes this really usable. Metric, it's big change. When you measure temperature and pressure, which way you can just rates, but it's not simple to find one solution for all cases. The nice thing if you use eigenvalues, at least I have kind of the same order of magnitude or z. How do we configure the trait? How can we help you to do this? No, it's medically challenged to show it. And there are a lot of computational challenges. Also, when you're going to higher dimensions, how to compute these distance spaces. So I have to compute them. You compute things on the fly. You do this interpolation. So there are a lot of things hidden behind the scenes. Come back. My first slide. Simple visualization for complex data. Unfortunately, I didn't really give an answer. Maybe sometimes. Maybe not to a certain extent. Some methods can help. This is clear, but they also can help. Are these methods simple? Maybe I don't give an answer here. For me, maybe yes. Maybe you are thinking, oh my god, this was everything else simple. And in the end, there's nothing wrong with complex methods. You have complex questions, you have complex data, it's also involved. This is the end of my talk. Just have to think a couple of people, ensure all the implementations, all the images that we have seen was not spending of my group. I 100% of the pictures are generated in our group, and most of them was either these were sketches by me, or visualizations I've done with our in-house software and in Europe. That is, these are pictures. So, thank you for listening.
I really like the abstract visualization. But I imagine I'm a new PhD student in mechanical engineering. How long do you train me that I see anything but abstract parts? I mean, you kind of, application person, you kind of have to do everything you told us today backwards and kind of learn how to intuitively go everything backwards so that I can do it on a certain day.
But we are dealing with kind of things. Not probably gives this talk. What is happening behind the scenes, all this abstraction, they only come kind of in the advanced class. But before, I rather try to give an intuition. So if you are talking about generalize, I can easily say, think about something that you find especially critical. And they're very good. Looking at these cliffs, if this is their cliff, typically I say, cliff is a language of really have to do the thing with English. And even tried out kind of making it automatic, taking papers from their domain and automatically extract some relevant invariants and then figure out our space is respected. But we are quite quickly able to read and to spot things that are quite interesting. But, okay, this is lots of communication. Show me areas that are similar. First, I look at it, give often they show pictures, or forward, after a while, stop. Okay, that was something strange. Why is this? And I had this experience many times. Sometimes say, this is unphysical, this shouldn't happen. And this goes, technically doesn't mean anything. I think especially with mechanical engineer working with, after 15 years, I met him at a tensor workshop. So he was invited to the main scientists. So we were overdoing our tensor visualization just for ourselves. And then somebody said, oh, we need somebody from the domain. And he was sitting there afterwards, so that everybody had these ellipsoids, all slides. Afterwards, he came to me and didn't dare ask me, but where to do these ellipsoids? And I quickly clarified, and I was didn't dare ask him. It's not just stupid. Sitting there and I'm with the names of this, I don't get them. He's very open-minded, and he said, I really decided to work together anyways. I think probably the first kind of meeting was really just explaining our language. And after half a year, I with PhDs to this is really PhD. Using our method, I had PhDs and here, let's still working together. The highlight for me was 3 years ago. He invited me to the annual meeting of fiber reinforced polymers in industry in general. But really, no researchers knew. These were people from Mercedes, Bosch, industry partners. Then you get right before that, don't show the 2.1. You want to see the 2.1 at least on the what should I show? And here establish the concept, this industry, and we got 3D simulations of real enterprise of an engine of a car. And we came visit us in the shopping for a couple of days. And I think all in the expertise. Some people trade in living room, some people trade topology, some people trade in this and that, and everybody contributed to it and made a navigating story about that. And most of the people in the audience for my talk never really be doing this visualizations and things. It's a really liked. I came to the for the incredible this. So don't answer these ones.
It's that you refer to tests. Something the hydrostatic testing. Meaning if you have the principal diagonal elements of it's on the shear. So do you have any special cases or special stress states?
Sure, for
Especially say that map of all the glyphs that you had in one case.
you're in the axis that shows all these taking just a stress state and every which is these stress are very different. You can compute kind of the measure of stress. You can use something mathematical formulas to compute this.
So was the globes, the shape of the globes.
Exactly.
They were different.
Very different. It's called the minus piece, which is really there's this red and this green part, which is the difficulty of the lips and the last kind of tensile compressive forces. The other one, which was this green things, which can be white. This is the first letters of the names of the guys who divided it. So that's the most specific meaning, and this focuses the issue. I need to show these things because those things we could theoretically read these glyphs before this. Let's see, it looks different aspects. I wonder about the glyphs, just showing all these different glyphs that I used.
So we can mark that. So we get to essentially.
What do you think about it?
Yeah. So given a frame of reference, what does this mean? Given that tensors because we and then what? So if we talk about the eigenvectors, we're talking about the eigenvectors of this matrix.
You can formulate eigenvectors without using matrices. You could say an eigenvector. If I would look at the tensor as a mapping, this all vectors can map during the mapping to change the lengths. These are eigenvectors.
So the eigenvectors are the advantage that even if you change the frame of reference, the eigenvectors will one.
Exactly. The eigenvectors are really something that belongs to the tensor, the component. This is also the case if you're looking at the picture. But people don't think about it. The change in frame of reference, the vector that is 1 before can become 1 point whatever 0 to change the frame of reference. But nobody would have an idea to just visualize the x component of the vector field. There are exceptions, especially the x components of interest, but somehow because people have an intuition about vectors, they didn't do it. They would draw an error. This error has nothing to do with the components. The error points in something else. Sure, I can express it. It's not. But I've seen for tensor fields, the people start visualizing one component of the tensor. Maybe, for example, for the tree of a hole, they are really interested how are the stress directions and related to my hole. To know whether it break. It makes sense that in general it is. Therefore, I always think that is the first thing that a student has to learn, and if they do tensor field visualization, don't visualize it. Even so, sure, this is what we get. This is it.
It's just finding always get something.
Yes.
But so I not comfortable. How common is it to encounter select things?
There are examples like for stress tensor fields is typically symmetric. Diffusion tensor is also typically symmetric. If we are going to since we also look at is flow fields, but we look at the gradients of this is not symmetric anymore. But you can decompose any non-symmetric change in a symmetric part. This means it even has some meaning. So the symmetric part tells you something about the deformation, and the non something about the rotation. But always this mapping, you can always decompose this at first by about a ball, first I push it to the you always can first rotate and then push, then get a little bit different representations, and especially for vector fields, the application has a specific meaning, it's related to what is this and what is it. This decomposition makes a lot of sense. There are also attempts to visualize these asymmetric tensor field, however, it's getting a bit more. It's possible to show you here. But in most cases, we would decompose. Oh, maybe there's some adjustment. There are layers. And you have different kinds of in the sphere. And all of it that you use right with information if you want. I have to keep in mind you have to be right. So I implement this one slide, but often people just mess it up using the transposed transformation methods and things next. You already have this problem. You're looking at the fields. If we're looking at vector fields and a flow on Earth, the flow is typically in this respect to all of them. I think it's always just to think about what we do. It's solvable, it's not complete magic, it's just doing the right conversions so that you do it in a consistent.
This notion of community of practice. In different fields, you always have your own practices. Actually, that's what you teach. Would you consider visualization valued in everything? Would you suggest that visualization is one fraction? Certain community, package was
analyze. I can depending on the mathematics, you do not exclude fundamentals. But you don't need to use a graphics with videos to do also I think training also the visualization makes you see the fact that you should read to time to read the schedule plot and to know what to draw something pictures for me this is very natural. The year of formula and build mental images out of it. I had one experience with a PhD student. I explained this just and we wrote a formula on the board that your name is
No question that sounds clear again. I have to do this.
I'm already here for 6 weeks. Unfortunately, it's yes, last year was a pleasure. Yeah.
Back.
Yeah. Not in vain. Virtually.
Definitely virtual.
It's a yes.
Real also. Take care of yourself and have a safe journey. I recommend your food. Instead of a concept, say we have 3 components of Reynolds series. If you try the
Yeah, also vector log is
so typically what we do is we take the velocity back or vorticity, third operator, and then we put